Welcome, everyone, to this first public discussion. The idea is that we would like to now onwards bring some interesting issues and then discuss some deep science and possibly have a follow-up later with the real public who are working on this field. And today we will be discussing about flexible electronics with an idea towards if we can impact the textile and combine healthcare to some extent to textile. And Samit, it's our pleasure that Samit will give open this session. And I will also add a little bit at the end. I have done a little bit on this area. So a brief introduction about Samit. Samit Chakraborty. He's an assistant professor at the University of Leeds. He has a PhD in neurophysiology from the University of Cambridge. He has researched in Columbia University, University of Copenhagen, University of Manitoba, and very early days in Auroville, Pondicherry. So Samit has a very keen interest on citizen science, and he has been very vocal and active on various aspects of citizen science while doing very, very strong neurophysiological as well as various different other kind of research. And one of them is flexible electronics and its connection to textile. So without further ado, I would just give the floor to Samit to start, and it will be an informal discussion. So we can interrupt at any point if the speaker allows. And at the end, maybe after half an hour, we will open the floor for completely open discussions so we can have discussions. And later we will post this maybe in YouTube or somewhere. Yeah, over to you, Samit.
Thank you those for the kind words. And yes, Auroville is something that not many people pick up on, but yes, I was doing biopesticides and vermiculture while there. Okay, so I'm a neurophysiologist, as Sid pointed out, but I'm going to talk about electrodes more than neurophysiology, but try and give you a context as to why we are looking at these aspects of electrode development. My primary interest is cerebral palsy. I don't know how many of you are aware of what cerebral palsy involves, but it's a disorder that is affecting a lot of children commonly. So it's a developmental issue, but it also leads to a lot of significant motor problems. It also affects skeletal system. So it leads to scoliosis. It can also be having some implications in spina bifida-like scenarios. So there's a lot of little things that are added onto it. And you probably have seen children with contractions. That's a common feature, as in the sort of therapeutic intervention is to do a surgical intervention and then to put some contractures to try and restore their limbs back to what we think is normal. My research is primarily trying to understand what are the changes and can we actually help improve function without having to, do the surgical interventions, because our working hypothesis is something very different. And that's where these tool sets come in very handy, because one of the current scenarios is, if you think from an Indian perspective, especially, the people have to come in all the way to the town to go to a clinic for a short period of time. The clinician has a very short period of time that they can spend with the patient. So you want to gather as much information as quickly as possible within that short period, get it analyzed and transferred. So that's one scenario. That's a current environment, if perfect. If not, you want to provide a system which allows you to capture the data without sort of interfering with their daily life in their home environment or whenever they're doing whatever they're doing. So we are sort of working towards a second goal, because we don't think we will be able to train up as many clinicians in a certain period of time. So, but this is probably quicker. And again, this is where I think textiles would be useful. Before I forget, stop me at any point if you want to have a conversation, and I'm happy with that, okay? So what do we record commonly when we're recording from people? We also do animal work, so, but I'm not going to touch upon that much, but that will be more towards the end. I'll give you a quick example of a few places where we think we can do implanted tools. What you're seeing on my screen is basically an EMG. Let me see. So these are two different electrodes. This is a commercial electrode that is standard silver chloride. This is a PEDOT-PVA, which is basically a polymer based electrode that we've been working on and developed with a collaborator in China. And you find these are activities recorded from the biceps muscle. So that's your muscle there. So anytime that's active, you're recording a signal. When it's not active, it's quiet. So all it's showing you that they're fairly similar, everything works nicely. These kind of signals is what we are interested in. And one of the things that we are looking at is the frequency at which they occur, the resolution at which we can capture them, and so on and so forth, because we are interested in looking at some sensory signals, which may be at a different dimension, but it's not necessary in the clinic. This is more for research purposes. But that's sort of where we are coming from. And the signal to noise is pretty good in these cases. It's not always this great, especially in the Indian environment because of humidity and temperature and heat, the body heat, everything changes, okay? And that's something to keep in mind. We are doing PEDOT-PVA. One of the reasons is this polymer can tolerate temperatures, something that many others don't. So a common one is PDMS. PDMS gets soft at about 40 degrees. It gets squishy. So you can't really use it. These are some of the tools that, so the top image is the fabrication that they're doing. And this is one of the ways that we have attempted it, and the collaborator has tried it. You basically put it onto a fabric and you can stretch it in any way you want. Our goal currently is this. So this is a printable circuit. This is printed onto the skin. And what we are trying to do is, can we build in amplification systems and everything by just printing it, by using printable ink. And so there are various ways of thinking about this tool set. And this is just some examples of where these kind of polymers have been used. And this is the polymer that we're referring, not the polymer, sorry, the metal that we're referring to here is nothing but gallium iridium. So it is soft at body temperature, and so it's easily malleable and sort of really conforms to the skin. The choice of polymer is based on what is biocompatible and also is easy and smooth and soft. Standard recording systems, this is what normally you'll find. So these are wet electrodes. They sort of sit on the skin, and you can see a metal there. Currently, there are textile systems which are using these electrodes. They're literally sewn in, but there's a problem with them. And that's sort of illustrated here. Ignore all the impedance measures and everything else, but yes, Sid.
Yeah, before we go further, so can you please explain a little bit about this new polymer you mentioned, this PEDOT? So what is it, and maybe is it silicone or is it something else?
It is silicone based, but it's doped with a few other cheeky things just to make it smooth. We have some. I mean, it's trying to reduce its conductivity significantly, but at the same time making sure that the pore size is not such that even with heat, it does not expand as the liquid comes out.
Okay. Yeah.
So we have that kind of, so, and we are also doing an encasement. It's a paper that's in the process.
And in terms of its porosity, so PDMS has this problem of water being yeah, so absorbed inside it. So it's very porous. So is it also similar or?
It is highly porous, but it does not have any problems with the water, is what we have realized, at least with sweat. And from what I know from my student, he did take showers with them on, so it didn't affect it.
So this is so you have to again cure them as normal PDMS.
Yes.
And it
Yeah.
comes with monomers, and then you have a cross-linker, and then yeah.
Yes. So basically, I mean, but it's still faster than some of the other methods. So it takes us about 2 days to make these.
That's great. Yeah, amazing.
So yeah.
And maybe
Yeah, Moumita.
Yes, Samit, you mentioned if you use PDMS in case of the polymer, whatever you are using.
Yep.
So you see that it becomes soft around 40 degrees centigrade.
Yep.
So you are expecting the temperature, the body temperature will be 40 degrees centigrade.
No,
and,
body temperature is going to be higher. So
okay.
Because your normal body temperature is 37 in the Western world, where we are, our outside room temperature is 20 degrees, right?
Yes.
And the squishy scenario was I was traveling in India, in Chennai. They didn't have pocket, and it came out like a blob.
Okay.
And so when you put it on the body surface, now the body itself is 37. The external temperature is around 40. So your interface is going to be in the 40 plus range now. And in addition, you have electronics and you're capturing signals. So you're going to generate a bit more heat. So that's where the problem starts coming in, is that these things become, they deform. And one of the areas where we were interested in is applying it for amputees, for prosthetics. So if you're putting it onto a surface, and PDMS is not very good with sweat. I mean, those are different. I mean, there's a lot more issues with PDMS than what I just mentioned. So PDMS does not.
How thick are your electrodes? I see the patches.
So these ones, these are big. I'm going to show you the electrodes that we are actually making.
Okay.
Those are up to, I think, the thickest we have used is 2 millimeters.
Okay.
But the PDMS that we were making, we did, I think below 2 millimeters was harder because of the electrodes pushing through. PDMS is a bit too soft, is in some ways. So, but the liquid metal does not stay in the PDMS too well. So there were lots of little issues with the PDMS. So we went for this P-dot PVA polymer. And now they're improving it a bit further by doing some cross-linking changes to improve the stability and conductance, because we are running into issues of depression, and then the encapsulation makes it really regress quite a bit. So you're now trying to figure out how to change that. So yeah, we can, yeah, those are a lot more interesting.
Why actually I asked you these questions, because I had done some work with PDMS.
Yeah.
And the thickness was, yes, around, for our case, it was around 10 millimeters. And we did not use it for any measurement on our skin, but the seal guard, actually what we use to make it harden. So I think that ratio was quite good enough, and we did not see any this kind of deformation. We were doing the experiment in Bangalore, and that was also that humidity and temperature was quite hot. So like in August, that time.
Yeah, so what we want to make sure is it remains soft. We don't want it to harden. We, in fact, so I'll come to, so that's the issue that we are trying to argue here, is that if you look at this figure here, which I have in B, that space creates an impedance, excess impedance. So your signal to noise is going to change completely. Signal drops dramatically. And that was the issue that we are trying to get away from by using soft electrodes. So we wanted them to remain soft, but then if you keep them soft, then they get mushy. So it's a how do you balance the two? So that was a conversation that we were trying to get into. But these electrodes, the ones we are just showing you here, are just to give you a sense of what are the current electrodes that we routinely use. These are wired. And they are the standard stuff in the clinics and everywhere around the globe. Although in our labs, we basically use, the buttons that you use first. I think I've spoken about this with Sid at one point, that you just the push button, like on raincoats, you literally solder a wire to it, and that's a good enough electrode. It doesn't have a perfect signal to noise, but it's good enough for getting some data out of it. So our key thing here, when we're recording EMGs, is if you look at some of these muscles of the forearm, some of them are really, really tiny. So we want to be able to get that level of resolution so that it's clean enough to tell us precisely which muscle is the problem. The common recordings are from these muscles, this large one here and this one here, which are the FCR, ECR. So if you're looking at it, you're sort of going these two. But we wanted to go for the smaller one. So that's another additional issue. So with the PDMS, we couldn't get to that resolution with the electrode size. There were some limitations in how the interfacing was working and all that. So when this came in the picture, we went for it. So if you have a solution which uses PDMS, but we are again going away from PDMS. We are now talking to a group in Kharagpur to see who are working on polymers to see if they can develop polymers using local material rather than polymers, which are, PDMS is petroleum dependent, isn't it? If I'm not mistaken.
Okay. Thank you, Samit.
So, sorry, Sid.
Yeah, so I was just saying PDMS is silicone. I think one of the things maybe later part of the discussion later on we can have is that I know that Moumita has a very interesting proposal on kinesthetic haptic using nanomaterials.
Let's discuss. Definitely.
Yeah, maybe Moumita is discuss.
So we are working on a closed loop on kinesthetics at this point. That's a separate project.
Yeah, sorry, please go ahead.
Okay, so this was basically just to show you the differences in the current system. So all of them have this sort of a gap formation that leads to problems. Oops. So I can't mute this, unfortunately. So these are the current, so this is ours. This is a previous version in the lab. So this is what our electrode looks like currently. The lower trace, and you can record with it afterwards as well. Okay. So the first part, it's already a published article, not from me, but the group that we are collaborating with. And if you watch, it can stretch, and it's all because of the liquid metal primarily. I'm not able to mute this. Why? I don't know.
Hear anything anyway, so don't worry. So no sound is coming through.
Oh, you can't hear anything. That's better because it's bothering me here. So if you look on the right on the left-hand side, my left-hand side, so of the screen, you'll see the fabrication and the description of the conductivity and all that, what we're doping it with and all that. Below is how it looks on the biceps. Okay, so for some reason my mouse has decided not to work either. This is brilliant. Give me 1 second.
But in a very discrete manner, not continuous manner.
Sorry?
It moved, but not in a discrete manner.
Yeah, I have no control
in a
on
discrete
it.
manner, but not so it's not moving very.
Yeah, suddenly yeah. I don't see it.
It's fine. Then you can go ahead without it.
Anyway, so you know where the biceps is, and you can see the band. And so the idea was that if we have multiple channels which are small enough, we can pick up fiber distribution. And something that we are interested in, because each fiber is recruited differently within a given muscle. currently all the muscle recordings are done by recording from a single spot. So you put an electrode on this muscle and you'll record the activity of that whole muscle at any given time. What we want to do is identify different regions within the muscle, because we know there are compartments within muscles. They are energy dependent. There's a lot of little things that we are curious to see how the recruitment changes, because we know when you're doing a task, the way you do the task changes depending on the fatigue level of the muscle. So all of these factors can be mapped up. So that's where we are heading with this. Let's see if this, okay, there we go. So that's my student with it on his forehead. And he walked around with it for 40 days. The top, there we go, mouse is back. So that's our electrodes. That's the standard commercial electrodes. What you see is this is when he sort of tries to wrinkle his head and all that kind of thing. It lasts for about, I think it was 10 seconds or something. And so each burst is roughly 5 seconds. Not 10 seconds, sorry, about 15 minutes or something, it lasted, and then it falls off. Our electrodes stayed for 40 days. There was no issue. So that was one of our arguments, is that we want to have an electrode set that can be kept on the body for a while. The recording, however, does not last very long. It lasts about 3 days. It's very good. The signal to noise is really good. But then the signal to noise drops after about, as you can see, after about 5 contractions in this scenario. But in a normal, if you just leave it on, then it's in about 5 days, it kind of deteriorates quite a bit. So overall, this polymer does a great job. The liquid metal helps. So now we are trying to use these as a sort of standard to see how we can use this. So this is just to give you an illustration of what we can do and what the other systems can't do. So the top trace is the commercial. This is what we are using. So this is giving you the recording from the locations on the muscle, the 2 sets of electrodes. This is what a typical flexion is, where you're basically lifting a dumbbell in this case. And you can see that you can pick up a shift. That shift is what we're interested in. And that shift basically tells us that the muscle is fatigued by the end of it. And being able to detect fatigue is quite important, even in a healthy subject, because now we can say when the muscle's about to tear, or tendon tear might occur. So this was quite interesting, because the commercial tool does not quite give us that resolution. Part of the reason why the signal is so good is that it's closely in touch with the skin. And one of the things that we haven't talked about at all, is that when we put an electrode, I don't know if you picked it up in the first slide, or the second slide, where the normal electrodes are showing you. Maybe I can just go back quickly. There's a wet gel sitting here, and that's crucial for being able to pick up a signal. In ours, we don't have that. We don't need any wet gels anymore. We just can bring it onto the skin, and it just, you record straight away. So we don't need that liquid gel to improve conductivity anymore. And that's a big step, because it reduces the work time. It reduces the amount of time it takes for putting the electrodes on. This can be applied on anybody without having any knowledge of it. You can just slip it on, and if its electrode sizes are right, we can pick it up and go by that. And we have other tools in the background which allows us to know who's wearing the system now. So we use AI tools to detect that. This is showing you now. Our previous one was using just 2 electrode sites. Now we have 64. Sorry, this is 24. And we're continuously mapping activity in the biceps. And as you can see, this is him doing the task. He's lifting the dumbbell up to his shoulder, and it's a roll up basically. And that activity is reflected across the muscles and the fibers, not just the muscles. In this case, only the biceps, and within the biceps, there is a difference in the way the system works. Sort of the recruitment changes, okay? Elbow to shoulder. And that is visible now for the not the first time, but more or less with a higher resolution. For us, it's the first time. This information is quite useful. So RMS, median frequency, and mean frequencies are the three frequencies that are three measures that are commonly used, and we've employed them. Mean frequency tells us just the activity change. Median frequency tells us about fatigue. And you notice that at a very high peak, you do get some degree of fatigue towards the sort of shoulder end of the system. So this is the shoulder, this is the elbow. So essentially, we're able to get a lot of information from these flexible electrodes. Something that intrigued, and this is something that we haven't officially announced it yet, but it's we have a competitor in Cambridge, so please keep it quiet. A very strong competitor now, who actually published a paper without telling us, but asked us for help, which was unique. So this one is essentially showing you something that we came across just by chance. So these peaks are essentially tendon activity. And there are no neural signals or any kind of a signal that is coming out of a tendon other than a signal going to this system. But tendon muscle interface is a big issue. That's where tears happen. When you're fatigued, that's where the tear is occurring. When you have a spasticity, that's where the tension is. So when you talk about a hamstring tear, it's commonly a tear that is because the tendon can't take it anymore, it just tears off. And it's commonly at the junction. So the easiest method that the orthopedic surgeons commonly would apply, they'll go in and suture it with some plastic-like material, which is commonly used for replacing tendons. But no one ever bothers to test it to see what the changes are. This is, in fact, one of the first times that we are able to see it, and you can see the 3 points, and we now know why they are there, because these are these three. And when we sort of do a flexion with our biceps, with our elbow, you essentially, if you feel it, you'll feel the tendon shift towards the higher. The belly moves, and we are able to pick that up. And that is a big step in the sense it's allowing us to assess the transfer within the muscle. It's allowing us to assess the local changes that are happening at the muscle tendon interface. And all of this is only feasible because we are very close to the muscle. None of this would be happening if we were using a standard electrode, because it would probably fall off halfway through, and we've had these problems. This is why we went on to trying to develop these electrodes. And that's my attraction for considering how textiles can be useful. So this is, as you can see, you probably have guessed by now that I've stolen my student slides and modified it a bit. So we're thinking of sports, we're thinking of diseases like scoliotic patients. And this was a project that we were going to start with a textiles group locally, but COVID didn't help it. We are looking at monitoring sports people, you in the gym, and at the same time being able to use it for prosthetic work. So there's a lot of potential use. We are now developing a stimulation tool as well, and that's why when we mentioned kinesthetic and haptic, yes, we are very keen on it, because that's something that that's my favorite conversation to have. But this is some examples of textile-based tools that are currently out there. So this is for sciatica, back pains, and scoliosis. This does not employ any EMGs. It does not do any of that. It's simply, you strap yourself up and you tighten it. It's almost like a corset. What we were considering, is if we take this and we take some of these technologies, so there is other tools out there where people have embedded electronics into the textiles, and you're able to use it as photovoltaic cell to generate power, or you can use it for EMGs, and these are some of the EMG ideas that people have played with, but you can see that they're all pretty bulky. There was a group from, I think it was Canada, who developed a suit from University of Waterloo. You can't find them anymore. Not sure what happened, but they seem to have disappeared. These are the typical electrode settings that people use for scoliosis to measure back issues. What I'm basically thinking and dreaming of is replacing these with a garment where either it's my electrodes, or we have conductive polymers, or we have something woven in such a way that they're really close to the body, and all the person has to do is slip it on. And it looks fashionable, it looks normal, nothing's unusual about it. So nobody has to second guess what's happening. And if you think of children with cerebral palsy, that's a big, major social hurdle not you've taken away. You've got them something, they're wearing something that nobody else, is wearing. It looks cool enough, but at the same time, it gives us a signal that we need. The fact that I can record for up to 3 days, okay, I'm dreaming that if it becomes a textile, it might last longer. Even if it doesn't, if it gives me 3 days and then next 3 days, there's another set, I still have a continuous 3-day data of them doing daily activity, which immediately is better than them coming into a clinic once every 3 months for 45 minutes, right? So you now have a more or less continuous set of information about what their state of health is. Let me see if I can share. So this was going to be invasive, or maybe I'll show you a video in a minute. So this was just to give you some of the other ideas that we have played with. We have made these in the lab, not the other side, but the ones on the brain. We have played with these. These are made out of Kapton-like material, and we inlaid it with gold, and then we have made them into flexible and different types. We have used these for making nerve electrodes. This is something from papers, not us. This is just to show the graphene types, which we don't use because graphene breaks. And so we have avoided graphene so far because it's flexible, but it cracks up, and so the impedance goes up. And once you have implanted them, it becomes harder to use. This is what we normally do, record from the spinal cord, and not necessarily on the side, but we go into the spinal cord as well. So there are lots of papers and people have been developing these. We have sort of pulled away from it because we've gone towards humans, but we still use in animals some of these kind of experiments and work where we record signals which are more single unit activity. It's a bit different. This is just to give you a quick feel for it. And personally, I think fabric-based, if it is a biocompatible fabric, we can apply them in these environments, because most of these materials, we want them to be absorbed by the body after a period of time, because you don't want them continuously there unless the patient needs it chronically. A lot of the scenarios is that the system will relearn. The system will readjust. So you just need to give it that boost or that modification for a short period of time. If you have to surgically remove them, which is what currently they have to do, you don't want that. If you think of it, these are the kind of tools that are currently being targeted and used for pain systems. For anybody in pain, you have surgically implanted electrodes. If you can remove them and provide a polymer, not a polymer, okay, let's call it a polymer, but it's a fabric, which is, let's say, biocompatible fabric, an organic material. You now have a system which can be easily implemented without multiple surgical interventions. So that's where we are hoping to be heading. We took a step back because this was harder, because it's UK and animal work is trickier. So we went for non-invasive because non-invasive human work is a lot easier and the outcome is much quicker. So overall, social impact is immediate instead of with the animal work where it will take us 10 to 15 years more. I'm going to stop sharing this and I'll show you something that we are currently developing with a startup. Give me 1 second. If I can. No, where is it gone now? So it's a ex-postdoc of mine, and I'll show you something. So let me see, where's our sharing gone? So what you see here is another idea that we are playing with, where we've got multiple recordings. So can you see the screen now?
Yes, we can. Yeah.
Good. So you can see somebody rocking on his, standing there and sort of moving his legs forward, backwards, and then side to side. And we got some signal being seen on the side. It's not the same set of electrodes. This is just a prototype that we're playing with to see, can we capture as much information as we can? And you can see he's wearing a football shin pad. But that's where all the electronics are sitting. But if you think of it, if you can make a simple glove or a sock where all of this can be embedded within it, you have reduced all of this need to carry all this load with you. All you have is you slip it on, you walk around like normal, all this information is gathered. So this is, we are working towards fatigue, along with autonomic nervous system data, like heart rate. We are trying to pick up circulatory system, oxygen levels, and various other things. The idea was, can we use something for sports, but at the same time, this can be applied in clinical environment in the future. So these are some of the ideas that we are playing with. In terms of extreme ideas of textiles, we have also got a plan where we have 2 projects right now where we're looking at, can we make muscles? So an exoskeleton that is based out of fabric. But then there's a secondary issue that comes in is, how do you make them such that they don't have excessive heat? So that's a bit of a, how do you say it? It's a very left field kind of an idea. It's not quite neurophysiology, but it's implementing neurophysiological thinking of graded recruitment and so on and so forth. But it's very far from what we normally talk about. But the idea for the scoliotic, that would be a fantastic scenario. I'll shut up there and let's talk.
Great. I think amazing some of the things you have shown. I think what would be nice that maybe I will show a few more things and then we can open the discussion. I will not show too much. I will take possibly 5 minutes or so, just to show that some of the applied aspect Samit has shown, and I have been discussing this aspect with
not my competition in Cambridge, I hope.
No, with Sambandhan, Sanjeev Sambandhan. Okay. He's IAC Cambridge joint faculty. Sanjeev has been working with this problem of so very much at the electronic side, where the aspect is to understand how good you can have the fluidity to not to have the breakage, the self-healing aspect. I think I'm one step below, down to the fundamental aspect. And my approach was that to use fundamental diffusion to read out signals. And I have been working with single molecules. So maybe
sorry, I didn't touch upon the microfluidic. Sorry.
No, I will not talk about microfluidic.
No, because we have explored that as well, but this is why we got talking in the first place.
Nice. So I think I have some little room to talk. but anyway, still I will not talk too much about microfluidic. But if my Zoom allows me to do that. So where is this? I could find my slide. I think the whole idea of this discussion is that to have almost like a brainstorming session and then see where we can go from here to the real application, which Samit is already doing. So let me see if I can. Okay, so this one, yes, I think this is the one.
So by the way, I showed everything to be wired, but if we can develop tools that are wireless and without needing any of these excessive need carrier things, that would be fantastic. So yes, we do have an interest in bringing in electronics and other tools if we can.
Amazing. So I got my slides now. So sorry about this delay. Yeah, so I think very simple. And I think it's more or less like this kind of picture. I mean, most of the time at the bulk aspect of electronics is from a statistical mechanics point of view, it's frozen, and it's almost like exactly the technical problem I have now. The movie is not playing. The cows are moving, but we can't see them. So it's good that the technical problem has caused, and that has led me to explain some aspects. So imagine that now these cows are moving. We could read out lot of things locally from those cows. Imagine those cows are our molecules of reading out molecules, and I think that's how even nature works in principle. Even in biology, all the cellular pores, cellular receptors are also working at that principle, possibly with a given a solution, there are a few interesting molecules and we want to use them to read out. So that is my deep insight for flexible electronics, but I'm not going into the nanofluidics aspect. I'm just going into one particular slide, which is related to flexible electronics. Is that, so now imagine those cows we are looking at them very, very far away. Those small dots you can see, white dots, are those cows. And now those are real molecules. I think this is one of the first observations, and I have confirmed with many people so far now, that the surface diffusion of molecules, and these are single molecule diffusing on surface, and we can see them. I can relate to the point when Samit was trying to measure things from the surface, and now the highest resolution is possibly at this length scale where we can see individual single molecules. And I think I mean, not only just looking at them, but if you look into some of this analysis. So now imagine that, so you all know high school physics, right? So one person will have a particular mass, and he will always have a particular, given a particular space, he will have a particular mobility or diffusivity, if I want to call that. Diffusion is coming from the word where you can move around freely. And so if you can have a coefficient which defines that terminology, diffusion coefficient. And so mobility is a little electrical terminology. I'm not using that. So now what we can do is that now every individual will have a single diffusion coefficient, right? So now what we saw in the earlier slide, that these molecules were moving around, and those are all same kind of molecule. I should not say same kind of molecules, same molecules, identical molecules. It's a commercially manufactured. These are dye molecules. You get it very, very pure, dissolve in water or other solvents of interest, whatever you like. And then you should not expect any change of diffusion coefficient, right? But what we see here is that now we are tracking one particular molecule on a surface. So now this is the kind of setup. So from the side view, we are looking at it, and you expect them to give a constant diffusion coefficient. Now, if I analyze one single trajectory out of zillions of trajectories we have, like this kind of cases where we have trajectories being simulated, and now they're going off slowly, you're seeing a shadow effect, and they're not being tracked anymore. So if you see one molecule, we are tracking, it's so long that at some point it's less interest to you, and then you're not tracking it anymore. So now imagine that for a particular amount of frames, let's say 80 movie frames we have. Movies are made of pictures, nothing more than that. So they're not fancy things. So you take pictures and then you stitch them, they become movies, right? So now you have taken pictures of these, many pictures of these moving molecules, and you do certain clever ways so that you don't lose the molecule from the previous frame to the next frame. Okay, so there are tricks to do that. It's very easy. You just need to do the time resolution correctly done, and time stamping. So it's not so difficult. Let's put it that way. So now you don't expect within a single trajectory. So that means when the molecule came in the frame, and then when the molecule goes out of the frame, it can happen, right? So molecule can, like in the simulation is happening, it can happen, the molecule goes out. So within that single trajectory, you should not expect for an individual particular, because the molecule remains same. It's not changing itself. There is no reactions. It's not becoming a bigger molecule, a smaller molecule, a different entity. So molecule is remaining same. However, now in the analysis, what we see is that now this is the starting point of the molecule, and it moves around here and there, and then suddenly it changes its behavior. So it becomes red. So all these points you see, these circles, those points are where the changes are being occurred. So we call it change point detection. So now very nicely you can see that now we are decomposing one single trajectory into multiple trajectory, but again reminding you that this is coming from the same track. Okay, same molecule, same human being, same cow started its day and came back home, but it's become a different person, possibly tired, something else has happened, some accident has happened, something happened, and it's a different entity now. So the molecule remains same, but the behavior changes at different frames. So this tells us that we are exactly picking up individual molecular forces or molecular interactions on the surfaces. So this is a very interesting aspect, I think, which is, I think, technologically we are at a stage at this kind of resolution. I don't think we can, at least for several years down the line, we can't go beyond this kind of resolution where we are seeing individual molecules. Possibly we can go down to even atoms, but biologically molecules are more sensible, I think. So I think, yeah, so that's what I wanted to show, and I think open the floor for discussions that I think Samit has given a very nice overview of microfabrications, microtechnology, and flexible electronics. And now I have possibly given a far-aimed nanotechnology, which is even molecular technology. So with that, maybe if we can make use of some interesting technology, that would be interesting in terms of textile to read out from the surface, from organs or anything. So I think, yeah, so without further ado, I'll just open the floor for discussions, and let's just have wide-firing questions. Yeah. So everybody unmute yourself and just ask questions. Yeah.
So the question I have is, I like the idea that you can sort of the mass concept, and then you're able to observe the molecule. So you're not looking at a z-axis here, or is the z-axis so small that it's not?
Now this is surface. So the trick is that optically we are using a evanescent field or
Right.
Total internal reflections. Very simple high school physics terminology. We know that, right? So we have surface waves of light. We are putting it in angles.
Okay.
So, but even then, if this surface diffusion was not there, what you could expect is that it's almost like you take an ocean and the fishes are moving around. So if you take a slice of that, what you will see dots, right?
Yeah.
You
No,
see
because
dots.
the reason I'm thinking of that is that if we have, so I like the idea because one of the things that we have been tinkering with and trying to think of is where microfluidics was coming in is, can we detect molecules like biomarkers for disorders? We talked about this at one point before. When you sweat, you release proteins, but we normally don't pick up any of that. If we can pick up these shifts in that using some of our electrode systems, because we know ALS, Parkinson's, all of them have some markers. This would be an easy way to do that. And
It's a very important thing for misfolding disorders. Yeah. So
cancers,
so I think so I think
cancers we can do that.
Yeah, so I think that's where I would be very much, even as you know, that we have something called universal. I mean, I like unifications and universal devices. So if this can be, now we have done optical readout, if we can also, so it's very complex, right, here at this point, because it's interacting with the surface. There is electrostatic interactions, and we are reading out optically. So that means electrodynamics is also important. The electromagnetic waves are also important. So, so both are there. Along with that, there are defects, topography on the surface. So biologically speaking, it's a very simple setup. So we have a glass surface, but now quantum mechanically speaking, it's way more complicated, because unless and until we solve these complex interactions, it's going to be, I think that's why biology becomes very, very hard, because there are so many complex interactions. It's very hard to read out. So I think we are at a very, very starting point where we are able to see this decomposition of electrostatics and electrodynamics. Now we change the Debye layer by just changing the pH. You can change the screening distance and all. So we change.
Have you explored the possibility of bringing in more than one? Because right now you've just identified using a dye.
Yeah.
If you bring in more proteins and see what the interaction looks like, because if you see a mass shift.
Yeah, so we have done so the next step should have been protein, but we haven't done protein. What we have done SUVs, small unilaminar vesicles, and some viruses, some pseudoviruses of SARS-CoV-1 we have tried also. So yeah, so I think when we did that, we found that it's really complicated to understand what's going on. So that's why we are publishing this one at the moment with this one, and then next one we have to do a lot of simulations to understand that what's going on. So we can give a disordered potential. Sorry, some jargons here, but so the surface is rough, so we can give some disordered static potential there, and see the evolution of the molecule. So to some extent, Chinmay is doing a little bit of molecular dynamics now, so maybe something he can also pick it up later. But Jan is doing this also in Cambridge. Chinmay is doing this in Bangalore. So yeah.
Because
so
if you're using a bilayer and you're using a vesicular system, you could even implement that.
Yeah. So I think
bilayer kind of a
yeah.
Anyway,
so I think
we can think about this.
Yeah, so I think one of the things, I have only shown you one exemplar result. So now even if this is mind-boggling. If you see you imagine H2O, okay? So simple water is acting differently at different positions, is actually, so that leads to the thought process of how complex the whole natural systems are, that we are not even scratching the surface yet. So, I mean, when people say that why vaccines are not being developed so quickly and so on, so we still don't know many things. So yeah, so I think that's another aspect. Yeah, definitely. I think protein-protein interactions would be a very interesting aspect to do next. Yeah. So anybody else got any questions? Otherwise, Samit and I can always continuously discuss.
I'm very curious about Moumita's kinesthetic feedback.
Yes, Moumita, maybe you want to talk a little bit about your zinc oxide and your recent interest towards haptics. Yeah, maybe that's something. Maybe how much we can
Yes.
talk about. Yeah, of course. Yeah.
Yes, so I have developed some piezoelectric materials, nanomaterials, and which has very high piezoelectric response. And I have designed the materials during the manufacturing so that they can have this kind of high response. And I'm trying to use them for haptic applications. So I plan to use them. I plan to make a device and a flexible device. Actually, I'm looking for how we can go for a flexible device so that they can be put on top of your suppose the veins, or the if you take your hand. You have already showed one photograph of hand, and you had a printed circuit on that, I remember.
Mhm.
So if we can have this kind of arrangement on body, and the plan is this piezoelectric patches will take out the response from the veins, and
Why
and
would
then
you
they will.
why would you put it on the vein?
So it's a non-invasive process, and because I want to get the signal. I want to. That is the haptic application I want to go for. So if
No,
suppose if
as
some
in-
certain part is amputated for some person, and if he or she is not able to get the sense that how
Okay,
if that person has
so
that
you're going to
part.
try and go for the nerve, not the vein.
Yes, yes. Then probably yes. I have used the wrong term. Yes.
It's okay.
Yes, yes. So it will take the catch the or it will get the response from the nerves, and the
Okay,
final.
so let's have a solid conversation, because there are lots of little
Yes,
caveats already in
yes,
it.
exactly. Because Siddharth told that, and then I was thinking of how much I should talk here now. It's an open discussion.
But I
No,
think we can,
the reason being that if you have an amputation, the nerve starts decaying. So you want the nerve ending that is left there is too deep commonly, unless you do it during the surgery itself. So what you're often also left with is the pain fibers, not the muscle signal. So there's a lot of little caveats that one needs to explore, and it's interesting because we are looking at certain aspects there, and we are exploring vibration tools rather than electrical tools.
Exactly. Actually, you were looking for the vibration tools, and actually, what I am proposing, that is also a vibration tool.
Yes,
actually.
and that's why I'm attracted by the idea. But
yeah.
So there's a startup which is an ex-student of mine who started this in Bombay, LifeSpark Technologies. If you take a look at them, so he's developed a vibration tool which is for we have tested it for Parkinson's patients already, and it works. And this is stimulating the area where the nerves and the tendons are sitting, and that can activate. So this is not for amputees, but this is heading in that direction. But your tool can give us that sort of ability to sort of, maybe we can get in. If it's zinc oxide, then it's not toxic, I think, if I'm not mistaken.
Yes, and of course it will not be exposed as a material. So there will be certain layers on top of that, so that it's not environmentally exposed. So
we should be able to theoretically.
I think one important aspect here is that I think zinc oxide is biocompatible. So
it's only excess. It's only a certain limit. I mean, but I don't think we'll hit that.
However,
and also there is a catch, Siddharth, because as Samit mentioned that most of the time this humid weather and this salt, sweating.
Thank you, Moumita.
So I have already seen that zinc oxide cannot be stable under if you keep it in water for a long time, and if it is salt water, then also the
But
same thing.
there is also a solution that to do
Yes,
the
there is a
calculation.
solution. There is a material science application, and there is a, solution that how to keep them away
The
from
core shell
environment.
structure, yeah.
Yes, yes.
Yeah, so I think one important aspect in this case is that the resolution is very, very nice. That I think I didn't quite understand. I think, Samit, I thought that you are actually picking up electrical signal. So you're not.
Yeah.
So you said now vibration. So that's why I was...
No, so for the stimulation side of things, we would rather go vibration than electrical.
I see. Okay. Yeah. So
because with vibration, you can reduce the total power required.
yeah.
Yes.
And so that's the dream idea. And it also makes it easier for the patients because patients are scared always of electrical.
Yeah. Yeah.
Even before you stimulate, they think about everything else. They're in pain.
Yeah, Moumita, maybe you can let everyone understand the length scale you're talking about, the size and the kind of readout signal that maybe that can also give us some idea that maybe at the 5-10 minutes left, we can discuss quite a lot of application so that this discussion can, we know that fundamentally everybody is very strong. So maybe for the follow-up discussion next time for the public, maybe we can bring some viewers who can understand what's the kind of application. So some length scale and some resolution, if you can talk about, that would be nice. And maybe Chinmay, you can also ask questions. Why are you keeping mute yourself? So yeah, Moumita, yeah.
Yes, so the single nanorod, what I'm talking about, they are around 50 nanometer in, if I call a diameter, it's 50 nanometer, and the length is around 500 nanometer, 300 to 500 nanometer. So this is one aspect. And if I make an assembly of all these nanorods, so I can make a patch of 1 centimeter cross 1 centimeter. And that is the thing actually I am trying to look for, because if I go for a single device, sometimes it's difficult to catch up the signal or take the vibration signal. It's sometimes difficult because of the electrodes available. So, I mean, that's a technical perspective I'm talking about. But
when you say it's, so you're saying 1 centimeter, 1 millimeter.
Okay, the single nanomaterial is 50 nanometer.
Right, so 50 by 300 is.
Yes, roughly 50 nanometer by 300 to 500 nanometer, yes.
So, because if you're stimulating, you don't necessarily need it to be really tiny. Because the location, the stimulation site can be spread, because
yes, the surface area you're talking about, right?
Well, yeah, yes. Because we can play with the electrical charge distribution and we can do all kinds of.
Exactly. That's why actually I'm thinking of making a patch with all this kind of nanomaterials, which can be 1 centimeter across 1 centimeter, the area I'm talking about.
But how big you can make, Moumita? I mean, now let's say that you can have a much bigger reactor. So I think that will be dependent on the reactor size and the scalability I am talking about.
Yes, but I think that is possible. That is possible, though I have not gone in that direction, but I think that is possible. We need some effort on that side, but that is possible.
Nice.
So, yeah, I'm laughing at my cat.
Yes, I could see your glass water bottle.
She doesn't like it standing. So.
Yeah, okay, great. And in terms of signal readout, the electrical readout, what is it we are talking about? Voltage and amperes, Moumita?
So we should look for the amperes here.
How much you read out?
But no, you're using it for, if you're doing a vibration, you're stimulating, so you're delivering.
Yeah, so there should be a picometer per volt or meter per volt kind of.
Yes.
Unit. Yes. So your vibration is not got any amplitude to it, or does it have
displacement, right? Meter.
Yeah.
So the unit of displacement is in meter, right? So length.
Displacement. Yes.
Or you can, if we are talking about DC, I mean AC, then it depends on the frequency, of course. But
so the way we commonly use the frequency vibration is using a frequency and
Yes.
displacement measure, because then we can identify which specific nerve groups that we are able to target.
Sure. Yes, but I think the amplitude is important here, right? So amplitude in terms of meter, right? Length scale. That's
Yeah,
what
but well, we can always modify that. So what we often would do is we'll take a piezo patch and then add weight to it to change the afferent activation. Because if you increase the load, then you go deeper into the muscle, or you go on the surface. So if you think of it, your surface recordings tend to be of a different frequency, because like braille, reading braille kind of a thing. Actually, that's an interesting idea.
No, I think
If you think of fingertips.
Exactly. I mean, that's what we discussed in Moumita, I didn't mention. So the fingertips, actually, there was one of the ideas in the proposal. We have been discussing that to have these patches on the fingertips. So it's almost like the corrugations of the fingerprints, because even this is even smaller.
if it's
going to be like a heat receptors. So if we can do it like a heat receptors, I mean, all the pressure sensors.
Do you have any right now? Can you make me a couple of patches? I want them. I can start testing them next week.
I have on silicon. I don't have the on flexible substrate, but I have them on silicon.
Fine. As long as you can stick it with the masking tape on a person, we are fine with it.
No, yeah, that can be done, right? Because if it's a silicon, still you can fetch.
I have one electrode already ready, but another top electrode I have to. Okay, I think that can be done.
Because I have a student starting in January who's basically looking at clinical data, and we are using the same device that we have for the Parkinson's that I just described. We are putting that on different locations to see how the signal needs to be transferred. And the key aspect there is to see so we are recording daily activity, and we want to now introduce perturbation. And if we are talking electrodes that can give us that high resolution for cutaneous, which is what you're describing, as in skin response, that's the trickiest so far.
Yeah.
And if we can do that, we are essentially talking about, so if you think of your interactions in the environment that you're in, your sensory cueing is coming from the muscle position. It's also coming from the skin response, skin receptors. But the skin receptors is something that we cannot reproduce yet. We assume what they may be. We assume what the reflexes look like, but we do know that all the reflexes alter the moment we do a task. What your electrodes can give me is that tool that allows me to start assessing how those interactions really come about. Because then if you're thinking of application in an amputee, we know precisely what the pattern needs to be. Because right now, everything is based on what happens in a clinical environment or in a patient and under anesthesia.
Yes, always. Yeah. Amazing.
What we don't know is what is really happening because one of the silliest things we did in the lab was one of the PhDs who was finishing his thesis. So like, all right, there's a bit of time. Let's do some crazy experiments. We stimulated the hands and we can generate some reflexes. And we said, okay, now do an active task. The moment you do the active task, the same stimulus strength, which is sub-threshold, as in it's not producing anything, now starts becoming more effective and behaving like a very high stimulus strength response. So it's a very different behavior that your system is producing, which immediately raises the question of what do we so far understand? I'm not saying we don't know anything, but
I think this is also very close to the molecular aspect. Yeah. So I think the same molecule changes its behavior. So I think Ramin Golastani in Max Planck Institute for Dynamics and Self-Organization was still I think he's still in Oxford University. So he had done a significant amount of theoretical analysis when molecule actually changes behavior, and this conventional idea of diffusion and this mobility, so that changes significantly by doing its task. So I think that's another aspect maybe. Yeah, anyway, so I was just thinking about the fundamental reasoning behind it. But yeah, I think that's a great proposal.
Oh, that's interesting. Yeah, I mean, I definitely would be curious to have some because it is something that we are exploring right now, because sensory is something that we don't understand. We have no quantitative measures for sensory. So
Right.
if we can perturb at a level that we think is sensory receptors are working at, we now have a means to sort of start looking for resonating frequency bands or whatever it is that we may be altering. So I haven't touched upon that. We do record EMGs at a high resolution so that we can tease out frequencies within it. So it gives us the, so we can do a source separation.
I think almost we are end.
I think Chinmay has a question in the
Yes.
group.
Sorry, yeah.
Please,
So
Chinmay, I think you are very close to some of the farmers and close to the village.
No, he has a question
weavers.
for me.
Please, Chinmay,
yes, posted in the chat.
Can your device be placed inside human body? Just like which device are we talking?
The one you showed in the shoulder, like while doing the gym.
The shoulder. No, you mean the one on the biceps?
Biceps, yeah, biceps.
No, that's just a recording system. That doesn't do any delivery at all. So it won't act like a pacemaker. But we are
just like a,
but it can pick up muscle activity as well in the heart. Yeah, sorry, my cat is talking to me. Come.
So I think what Chinmay,
So
you're
if I
asking
understand
if we
Chinmay's
can.
question,
Sorry.
so if I understand Chinmay's question, probably he's asking, Samit, the flexible electronics what you have made, can that be used?
We can adopt that. Yes,
yes,
we can adopt that easily, and this is where again your haptic can come in handy, because if we can
for invasive methods, what he's asking.
No, but it's a transplant, so in that case,
it becomes a bit trickier. We know our material is biocompatible. I don't have full faith in it when it comes to stimulation.
Okay.
Purely because when you stimulate, heat is generated. The moment you generate heat, the liquid metal behaves a bit weirdly. And I'm not convinced by the material scientists that it is guaranteed to stay the same as
I think that's where I was trying to show this fundamental molecular motion, that I think there is a gap between this flexible electronics and material science community. This liquid metals, it's being used at a very, very high concentration.
Yeah.
And there are huge amount of heterogeneity in the sample. So that's another problem.
Well, it's the same thing that we realize when we are pulling, because one of my questions immediately was, is there an impedance shift? And they, oh no, it's not enough. And I'm going, I don't care if it's enough or not, because I'm going to generate eddy currents. If your liquid is moving around just by simple logic, you would create a backflow. And if there's a backflow, you're immediate, and we did notice that. So our EMG signals drop. If you're recording just an RMS amplitude, yes, it's not a problem. But the moment you're looking at nuanced behavior of the fibers, it becomes harder.
So maybe last part of the question, I think I would like to ask a few questions. So can we create some of the, I have seen very interesting amyloid fibers being created. Similarly, can we use our weavers technology to make some of these cables or wires or liquids?
So something I didn't technically tell you, but the person who was standing and rocking their foot, he was wearing an insole, which we made ourselves. So we tried making it using material that is bought. We landed up taking copper wires pulled out of standard wires, ripped it apart, and then, so that's what we're using.
Okay. Yeah.
Which, if we do it ourselves, it's easy to make, but if you have the weavers actually weave it in, you can weave it into anything.
Yes, exactly. Yeah.
And then it's not difficult because we literally made it by hand, like sitting down and putting it together.
Yes, I think that's it's great that we have this fantastic fundamental applied discussion. So it would be very nice next time if we can bring a real weaver on board, and then have, somebody who has a certain amount of interest towards science, of course. So we can't speak too much science there, but I think it would be very nice to see that because some of the things I see that there is again a huge gap, and I think if we don't try to bridge the gap, nobody will do it. So if we can at least give a little bit of our technology to them, at least help them, I think that would be amazing. So I think that would be another avenue, maybe as a follow-up. So maybe we would try to continue this discussion in future also for other topics. So we start with a scientific discussion, deep science, and then next one a follow up with a very dissemination, not even applied oriented, so that we can see where we can, at least the roadmap, if we can't even see in our lifetime, at least a roadmap where we can reach, or maybe if we are clever in our lifetime, we can also do something.
No, I think so. The interesting thing is that we have been exploring these already on the side, and it's not. And one of the things that I'm trying to figure out is how we can translate it into Indian environment, community-based rehab kind of environments. And so that would be a fantastic chance to actually start talking about these.
If you have any viewers in your network, please bring.
We don't have that in India. We have it in Pakistan.
Okay, they also do very good in Pakistan. Yeah.
So we have Pakistan, we have Nepal, we have Sri Lanka, but we never managed to get anybody from India.
No, I think it's very timely, because the text, some of the cases, if we look into Bengal itself, the Bengal tat industry, the handloom is almost extinct, and so I was thinking that, and there are government schemes which allows them to get money and then get going. So if we can help them, I think in a very open manner, so that I think
And I think, I mean, we have plenty of the closed loop conversations as well. So in terms of textiles, one of the things we can go for is something very simple, very basic.
Yeah.
And the haptics is an easy thing to do, because haptic for gaming is already out there. If we introduce that with a woven garment, which is conductive, all we need to think about is how do we implement things like an amplification system or a data logger. Because if you're going to use it for clinical world, we need to have a think. But I mean, those are things we can develop, because already we have already had a think and played with it, these application ideas already.
I think it's nice that we are discussing this. So maybe I will also mention one of the things I have been thinking, that from the privacy perspective, the encryption perspective, if we can use the saris as a Faraday cage kind of effect. So, I mean,
strangely, we have been discussing that for the SOC right now.
Fantastic. Okay. So I think there's also GPS and other issues.
So we have another tool that we are developing, which is a visual thing to eliminate. So I mentioned that when you pick up a glove or wearing a piece of clothing, we know which muscle is active and who is wearing it.
Sure.
We are doing that without asking you who you are.
Yeah.
So we have identified a signature within the EMGs, and we can use that to tease out. Oh, sorry, my cat's doing a circle today. Come on.
And then actually on that aspect, to some extent, Chinmay has started doing some Turing pattern modeling of complex systems, maybe something.
Yeah, I mean, because
if you have some complex signals, Chinmay is now becoming an
so we are trying to do it in real time.
Yeah.
So we're using LSTMs and CNNs currently to tease out, because our biggest problem is these are not image data.
Yeah.
These are time series data, and most neural networks don't work with time series yet.
Yeah.
So that's where we are on that. And so any tool that can benefit us, I'm more than happy to discuss.
I think with that, maybe we are already over the time. I thought of doing it 1 hour. It was very nice interactive discussion. I think let's just stop here. And maybe what we will do sooner or later, this will publish in YouTube, and then everybody can listen to it. Yeah, so I will just stop recording here. And